Hello there, welcome back. We're gonna finally decide to move on and talk about HNMR, or called proton NMR. And we're looking at the hydrogen with the one proton in it. In the normal situation, you can imagine this is like a sample. I have shown 3 molecules, but like millions of samples in a NMR tube you've seen in previous video. You can see the red arrows going up and down and sideways as well. They are the nuclear magnetic momentum, and if you look at them one by one, they're all random. That's how it is outside of the machine in the normal environment. Because hydrogen has a quantum spin number of half, there should be 2 quantum states that's allowed it by quantum mechanics, and they have same energy at the moment, alpha, beta spin. And their populations are also exactly half and half. Let's say this is alpha spin and that's beta spin when external magnetic field is given this way. Then we are placing them in the magnetic field, therefore they're not equivalent anymore, right? So they will start to split. As you increase the magnetic field from 0 to say 1 terahertz, the gap between alpha and beta spin states increases. I cannot show whole thing, but yeah. So this is the energy gap between the alpha and beta spin states, and that's proportional to the magnetic momentum and the external magnetic field, then the angular momentum, and the ratio of these two is the gyromagnetic ratio, right? So I said that the actual magnetic field that's influencing the hydrogen nucleus is not the external magnetic field. Actually, that's influenced by the local magnetic field created by electron densities. Depends on the types of functional groups and orientation. You may get positive value here or even negative value. And in later videos, we might have chance to get into the details of it for the major students. So as soon as you put the sample tube in the NMR magnetic field, they will start to slowly reorienting, most likely at the alpha spin state and some beta spin state. If you have a not extremely strong magnetic field, the energy gap is not big enough to prevent the thermal distribution. So this this spin's gonna move up this way and go straight up, and this will turn around, go straight up. This is already up. This will try to flip and go straight up, and so on. And some of them, depends on the energy gap, will stay as the beta spin state. And the spins are not on the plane, right? They are actually, it is shown like this, for example, pointing up arrow, but they could be going into the paper or coming out of the paper towards the camera and so on, right? Tilted this way, but it's not parallel to the paper. It could be in and out. They're all random. So if you combine all of those spins together, it may look something like this. I mean, you don't physically do that. You never do that in the real experiment, just for the sake of, recognizing their distribution, random distribution. Let me put them all together and see how it looks. So I have somewhat more alpha spin and some less beta spin, and the radio frequency is going to flip. It's more unstable. Sorry, the stable beta alpha spin to more unstable beta spin. Okay. Then the classical machine's gonna detect how much radio frequency has been absorbed. Here, if I show you the two different point of view, if you see it from the top for these spins, the spin, where the arrowhead is, the spins are randomly distributed evenly. So they're evenly distributed, pointing, different direction. And also the bottom, if you look up from the bottom, you'll see those random but evenly distributed spins. That's what I mean by all these are randomly distributed, but more to the alpha if they put in the magnetic field. So you can say this is the collections of all the spins when the sample is in the magnetic field. If it's not, they will be all equal population this way or that way, right? Say your machine at school is 400 megahertz like we have in our school for undergrad students. This is the energy gap you give to the naked proton of the hydrogen. But in reality, you have electron density screening the magnetic field using, we talked about it, but the electron density is creating local magnetic field in opposite direction to the applied magnetic field. So the actual magnetic field for the nuclei will be somewhat less. So energy gap will be somewhat less. Okay. Say this is the nuclei for this type of hydrogen here. That's close to the chlorine. You know that we talked about it, that electron density is less here due to the electronegativity of the chlorine takes away the electron density. We talked about this a lot when we were doing chemical reactions and the properties of compounds. In this case, only due to the inductive, but you know that if there is resonance, you have to always consider resonance to find out electron density. Then someone can ask you, what about these hydrogen then? How much energy gap you expect between alpha and beta spin? Well, you have more electron density around these hydrogens in all the samples, right? Regardless of their direction of molecule, spin stays the same. I mentioned it like an astronaut in the spaceship. Whether the spaceship is turning around or not, if you are in the air, I mean not air, but in the middle of the spaceship without touching the floor or grabbing onto something, you don't necessarily change your direction only because of the change of the spaceship direction. Anyway, so more electron density around the hydrogen creates more local, magnetic field against the applied one in the magnetic field. So you cancel more. Therefore, the energy gap is less. So it will be something like this, right? Less. So how much less is that between this hydrogen and that hydrogen? That's normally, this difference here is normally about, let me draw a line down here, is about ppm level. ppm to the applied magnetic field, parts per million. So the effect of the hydrogen electron density, as you can say, is very minimal. And that much of a small difference in those hydrogens, the NMR is able to detect, and we are using it to tell the different type of hydrogens, the alpha hydrogen, beta hydrogen, and so on. So that's the definition of the ppm. That's what we plot on the NMR as a x-axis ppm. That's what we called chemical shift. Then every hydrogen have different degree of shielding going on. So it would be useful if you have a standard. So the early chemists set up a standard with one of the most shielded hydrogen as a 0. So there is no such thing as a really 0 ppm, because basically, like I said, the ppm is the energy gap difference you create, right, by the applied magnetic field versus the difference between the hydrogen, the actual magnetic field reached in the hydrogen, but the usual difference between different types of hydrogen. That's the range, and there's no such thing as a 0. So what we use to set 0 is TMS, trimethyl silane. Let me show you the structure. Did I say tri or tetra? Anyway, so this is tetramethyl silane. It's kind of volatile. It's almost like a pentane. But because silicon has a slightly less electronegativity and it's a big atom compared to the carbon, electrons tend to give into the carbon. Thus, the hydrogen gets very much shielded. We set that as that hydrogen as the 0 ppm value, the standard. And that doesn't mean there is no energy gap, okay? You have energy gap, one of the smallest possible. I mean, not really the smallest possible, but it's one of the smallest one, like small gap, because you have so much electron density shielding the nuclei. Then the rest of the normal organic compounds, such as that, you have a partial positive, little bit of partial negative charge, but they are neighboring the carbon and hydrogen, not like a silicon. So their hydrogen electron density is somewhat less than that of these hydrogens. So shielding is less. Therefore, you get little bigger energy gap between alpha and beta. The more de-shielded one, like these hydrogens, right, due to the chlorine, they will have a little more energy gap. And then if you have more electronegative atom, multiple of them, then you can make them more de-shielded, so you can have a bigger, greater alpha beta energy gap and so on, but it can never be more than the naked nuclei, right? Thus, on the chart, we plot this way. If you go from the 0 to the more and more and more values of the energy gap, we say those hydrogen atoms with the more de-shieldedness are going downfield. There is a technical reason for that, but we'll skip that. And I'm not gonna explain the historical reason, which means if you go closer to the 0, the hydrogens are more shielded with electron, and the nuclei is not feeling as much applied magnetic field. Therefore, the energy gap between alpha and beta spin will be less. If you're curious, what if you are able to take Nmr of sodium borohydride or something like that, right? Lithium aluminum hydride, that those that has actually negative hydrogens or ionically negative hydrogens. That obviously will be the hydrogen more shielded than these TMS, tetra methyl silane. So the number has to be negative value, -1, -2, depends, right? So you can get the idea, and the like you can have negative value. Then usually how far you have this x-axis go in terms of a number, like not quite the naked one, but how far. One of the most de-shielded normal organic compounds can have around 12 ppm. So like, you know, when normal alkanes are around 1 ppm or slightly less, usually without electronegative atoms, those carbon hydrogens are normally 1 or less. So you may have a 12 times more de-shielded hydrogen you can create with the normal non-ionic compounds of organic compounds. So remember, you have equal distribution of alpha and beta without magnetic field. You put the sample in the machine, you have a polarization, and you have more alpha, so you are magnetizing overall molecules. Altogether, you have a more spins up, so overall you have a magnetization upward, alpha spin way. Okay, that's when you flip the beta to the alpha. But experiment wise, we are giving different energy light in order to flip the nuclei with a different amount of the electron shielding them. Okay, for these guys that's not shielded much, you need a lot more energy gap to overcome, so your frequency of the radio wave has to be higher frequency. If you reach to the 0, one of the most shielded one, they don't have a much energy gap, so your frequency has to be a smaller number. So this matches conceptually in terms of number wise. The ppm is the energy gap, that's the light frequency you give, but that's kind of opposite of electron density, right? 0, close to 0 means you have a more electron density. Close to 12 is less electron density. So it's opposite concept. But if you think of it this way, this is almost neutral-ish. And this way, you get more partial positive hydrogens. And this way, you have a negative, so you have a partial negative hydrogens. Then it kind of matches up with your concept of number. So yeah, the shielded hydrogen has a partial positive charge. So nearby you have some electronegative group. And the negative value, the hydrogen's negative because something is giving electron to the hydrogen. So I hope that helps you, and also imagining the energy gap. So magnetization, but radio frequency, flip the spin. Okay, that is the resonance we talked about with the IR and other spec. But later for the major students, we are going to talk about pulse. Okay. Then what's coming out of the sample is this type of mixed up different frequency of waves, free induced decay. Then we're going to be doing FT, Fourier transformation. Then we're going to come up exact same NMR as the classical one. Okay, that's upcoming for the majors. So this is hydrogen NMR chart starting from 0 to 12. When you look at your sample or expected product, you know you're not expecting negative value, right? So you can set the range of the NMR scan from 0 to 12. If you know in more detail, you may narrow it down to a certain range if you want to. But typically, we go from 0 to 12. Then I'm gonna split this chart X value into a couple blocks, say 4 and the 8, like we did for IR. And I can say from 0 to 4, they are usually the hydrogen that's on the sp3 carbon. So we are looking at the hydrogen nucleus, but how much it's shielded is determined by what type of carbon you have. Okay, so typically 0 to 4. Just like the in IR, the CH stretching, when the carbon's sp3, that was a 29 something to 28 something, that kind of thing. 0 to 4. We'll get into the more detail. And from 4 to 8, it is usually the case that you have a sp2 carbon, a somewhat more electronegative carbon bound to the hydrogen. So the hydrogen has less electron density. Okay, so electron density wise, you have a less here. Number one reason is because carbon's more electronegative. That's affecting the density of electron. But number two, you have a local magnetic field. Okay, in this case, you are actually making hydrogen fields more. So you are actually adding, like you have applied one, but you are actually adding some local magnetic field into certain structure. Okay, when they have thing called aromaticity, which we didn't talk about it yet. Yeah, one of the common example is benzene. But you also have some local magnetic field for alkene as well, but you have a significant local magnetic field built up by aromaticity, much more than normal alkene. Okay. Then what about sp carbons? Surprising, right? So you have sp carbon pulling hydrogen electron more than sp2, but it happened to be right here. So sp carbon holding hydrogen. So this hydrogen is more shielded than most of the sp2 carbon and some of the sp3 carbons. So you can say obviously that's not the factor of electronegativity. This became minor factor, and you have this local magnetic field taking the magnetic field away. So you subtract. Okay. So those local magnetic field is happening due to the phenomenon called an isotropic effect. So roughly speaking, this is it. Electronegativity sets the location, but then like in IR, we are having some variations. The variations caused by local magnetic field. Okay, so how does it work? You have to think about how the electrons are moving, because electron movement of the 1s in the hydrogen atom, that was creating the local magnetic field. But when it's bound to bigger molecule, electron now is also affected by the neighboring groups. And especially when you have pi electrons can move around more readily because they are loosely held and they have such shape of a orbital, and their orbital can have sometimes conjugation, right? If you have a conjugation, then you have a better chance of electron moving around. So those functional groups with pi bonds, like double bond, triple bond, you see the stronger effect of local magnetic field, the anisotropic effect, and they're working this way. When you have alkene, you imagine electron here in the center. They're not in the 2p orbitals, right? They are in the pi bond. So in this electron cloud, the electrons are circulating this way, not up, down, right? Parallel to the, perpendicular to the page, they're circulating this way. Therefore, you are creating the magnetic field that's going down and comes back, down and comes back. Okay? So if you see from the top, you can see carbons lying on the paper like this, and then you have electrons, the top one right here and the bottom one is below, and you don't see it. And this circulation is actually going this way. That's what I mean. When magnetic field, the external ones applied, not sideways, okay, on this molecule. The molecule is not on the plane, but like perpendicular one. The B0 is perpendicular to that, parallel to the node. Then you are creating the circulation on this plane, this way, okay? Then you get the magnetic field coming down through these electron density and going up outside. So outside, magnetic fields are going up. Okay? So when the molecule is like this, magnetic field is going this way. Exact same direction, parallel to the applied one. That's why you are adding up. So B0 plus B local. What's the net effect of these increased magnetic field, you recall that more electric magnetic field means more energy gap between alpha and the beta, so you need more ppm, right? Therefore, the reason for sp2 carbons influencing more on the hydrogen is not only the electronegativity, but due to the increased magnetic field. That's why they set apart from the sp3. Then benzene has, again, I'm gonna draw the imaginary paper perpendicular to this whiteboard, and you have a benzene sitting right on it. So benzene's perpendicular to the page. Then benzene has a 3 p orbitals. So I can see the p orbitals are like going this way, right? So when I draw, I have to draw like all of them are going this way, and perpendicular to this paper, which is the perpendicular one, so p orbitals are going this way. So the other side of the p orbitals are here, right, pointing under the paper, so pointing the other way. But that's a p orbital. So how do you imagine the pi electrons, not the p orbitals? The electrons are actually, when you imagine pi, and the pi's are all coming together. So you have electrons like, hamburger bun, you are sitting right here, and then the other electron cloud is down here. It's like a sandwich. You have a ham and the 2 buns, but one here, one there, okay, perpendicular. That's the benzene. The electrons are rotating, so I have to show the top view. So benzene now is on the whiteboard, and that electron density is right here, okay? And when the B is given like this way, for this point of view, the magnetic field is actually coming up, okay, coming up. We did this in the previous video, how to represent magnetic field that's going up and down when we did mass spec. When it's going down, we use X marks, right? So they're coming up because I see it from here, and electrons are moving then this way, negative charge. Remember on the mass spec, we have a positive ions, so they were turning this way, but now it's turning that way because it's the opposite charge. But anyway, that's actually doing it like this way here, over here, and you are creating much stronger, because you have so much electron current going around, and more effectively. So you got very strong local magnetic field, very strong. So aromaticity is giving them to do this job better. So this added magnetic field for benzene is much greater than that of the alkene. So in this block, you can say around in the middle, not exactly, but you have a regular alkene, and there you have a benzene structure, and the hydrogens on them, that's a lot more de-shielded than this, because it's not really more de-shielded, but it is feeling more magnetic field. However, the net effect is as if the hydrogen's more de-shielded, it is actually going more downfield, right? Downfield. De-shielded, but not physically de-shielded. Please remember that. Not really de-shielded in terms of electron density, but it act like it. It appears to be like that. Then what other hydrogens you have? If you remember the discussion on IR again, we had aldehyde CH, right? So aldehyde CH is coming around in the middle of this box at 10 ppm. So this aldehyde hydrogen is more deshielded, no doubt, because carbon has oxygen. Inductively, much more electrons withdrawn from hydrogen to the oxygen. Okay. But also you can see the double bond is having some anisotropic effect, electrons moving around, and then magnetic field is applied to it. So yeah, you have that as well. So altogether, it's even more than benzene double bond. So we can say that's due to the more electronegativity for aldehyde hydrogen. All right, so what's left? Remember we had NH and the OH. There are many different instructions out there, but I usually wouldn't go by the ppm. There are some special ones like amides and couple things that gives distinctive numbers, but I don't want to have you rely on those numbers. So here's my message for the non-majors. The NH and OH, as you know, giving broad signals. They don't have a one distinct quantum state because their bonds changes due to their strong interaction between molecules. So bond strength do changes. Therefore, they have a different electron density on the hydrogen as well. And I like to say that you can have NH and the OH. They are anywhere on the chart. That's more safe for the beginner. Then you'll see that they show you broad peak. Not always broad, sometimes sharp. Remember I gave you like free OH is giving sharp signals because they're not hydrogen bonded. So same thing, you can have a sharp peak or a broad peak. And most of the time, we didn't talk about it yet, but just put it down there. They don't split. They don't split most of the time. And one other thing is you can remove them or making them very weak by putting D2O. So they label. What you really do is, if you see something like this and you doubt one peak as a OH or NH, you obviously go for IR, right? Because you never miss them on IR. We talked about that. Relationship between NMR, IR, and mass. I talked about it in the intro video of the NMR, but yeah, you obviously will go for the IR. But on the NMR, you can also check if you drop one D2O drop into the NMR tube, then these signals will nearly disappearing. Okay, that's because D2O, as you know, it has a spin quantum number of 1 and the 3 states, so it splits more. So these NHs and OHs, they react with the D2O and then replaces the hydrogens with the deuterium. So the signal becomes much weaker. First of all, the nuclei is heavier, so yeah, it's not even gonna have the same frequency. Also, it has a more multiple quantum state and so on. So anyway, you're gonna remove them. Then aha, that's the signal that you just removed by adding D2O, and you run it again, and you check it, and oh, I removed this peak, then you know that was NH and OH. So how do they label on the spectrum test? They say D2O exchangeable. Okay, D2O exchangeable. OA exchangeable. For triple bond, the abnormal behavior, I said it was due to the local magnetic field, and there are two pi bonds in the triple bond, and one pi bond has the plus phase and negative phase, and positive phase and negative phase for the other pi bond. So the pi electrons are located this way. When you put this molecule in the external magnetic field, the electron is able to move around this way. That's how they explain. Okay, then your magnetic field is going this way and this way. So whether the hydrogen is on this side or the other side, and you know, if hydrogen's here, you will have a carbon chain there, and vice versa. Either case, as you can see, the B is canceled by this local, and here as well, right? You got canceled. You are actually subtracting this, reducing it so much more than, you know, I mean, this you add up, but this is reducing. So even, you know, considering the electronegativity of the sp carbon, the local magnetic field effect is more significant. So instead of this being here or here, it moved down in the middle of the sp3 region. But if you're lucky, sometimes you see some signal here. Okay, that's carboxylic acid hydrogen. And the OH can be anywhere, but if you see something here, that's what I mean, that can be carboxylic acid hydrogen. If you have OH peak between say 8 to the 4, right, double bond area, say here to there, you can assume that you have this type of a hydrogen OH. Again, I don't rely on that as much, but if you do happen to have, then you can assume. And here, yes, anywhere, okay, you can assume that you have a regular alkane with the OH. And how about NH? You can assume if you have amide. What is amide? Amide is like carbonyl group with the NH, or 1 or 2, right? NH or NH2. Then you can have the peak around here. So something in the middle here. Here to, what is the 7, 7? So around here. So you can say 7 plus minus 2. Okay, 7 plus minus 2. So you find the amide hydrogen in protein a lot. So this can be useful for you. Sometimes the amide hydrogen shows splitting. Okay. And again, the double bond, if you have a double bond with NH, so you have a benzene having NH, NH2, or even double bond NH or NH2, they come in around this area, around this double bond area. So plus minus something, just like the IR. And I don't even recommend you to trust these area, but I'm just putting it out there. Also, the regular alkyl amines, NH or NH2, this area. How do you know it's NH or NH2? Well, and IR gave you some different shape, but here you don't have that. What we rely on is Y value. Okay, Y value is proportional to the number of hydrogen. Not really, but Y value can be useful. But I go more by area. If you have a signal, any shape, right? Any shape of signal. Because if you do FT-NMR, the area underneath of this curve, this is like a graph by the function, right? So if you do integration of the function from certain number to certain number, integration from say 11 ppm to 12 ppm, you get the area out of it, right? Whatever the function of the frequency is, right? You get the area. That area is what we call integration. So instead of the Y value, actually we use integration as more useful information, and that's proportional to the number of hydrogen. Okay, integration is proportional to the number of hydrogen, meaning it's not number of hydrogen, it is proportional to the number of hydrogen. Let me write it down. Integration I is not number of hydrogen, it is proportional to the number of hydrogen. Usually you can say for the beginners, more Y value means more integration. Yes, if you don't have a multiplets, but if you start to have more than triplet, right, more splittings going on, then you cannot say Y value is useful anymore. It has to be actually integration number that you use it to calculate out exact number of hydrogen. But again, for the non-majors, I don't think you will get a problem ever where you need to figure out exact number of hydrogen. You can say the number given on the spectrum is the number of hydrogen. Somebody did the calculation for you. So last thing I want to say here is, before I wrap up for this video, I'm gonna come back with a part 2 of HNMR. Is how do you go by like sp3 carbon hydrogen? The alkanes have attachment. So then how do you read it? Well, the sp3 carbons, when you have a hydrogen there, it comes in this area most likely. It could go over, It depends on the electron density. So normally with attachment of a carbon and hydrogen here, if you have one chlorine, it could come around 3 ppm. Okay, so roughly speaking 3 ppm, but that depends on what you have here. So I'm not saying it is 3, but around 3 ppm. However, if you put one more chlorine, depends on the attachment here, but then this hydrogen can come in. Roughly speaking, around 5 point something, okay? Depends on what you have here. 5 point something ppm. Okay? And if you have one more chlorine here, then this hydrogen go into the 7 point something ppm. But that's not aromatic compound, right? 2 chlorine doesn't make it double bond, but it comes in the 5 ppm area. 5, where the double bond area. So again, the variations taking place due to the inductive, which is electronegativity caused, and the resonance, just like the IR, the location can shift a lot. So those typical numbers are the standard you begin, okay, your justification. You begin with these typical numbers, or sometimes these things as well, right? However, you should be aware that the numbers shift greatly due to the electronegativity of the neighboring group, or the double bond presence, or the size of the ring. A lot of other factors we talked about with the IR applies here. The main thing is you go by the electron density of the hydrogen and you have to justify it. So guideline is anything more electronegative than chlorine, it should be more than 3.0, meaning around here, right? 3 point whatever, like oxygen, fluorine. But if you have 2 oxygen, then way below here. So it doesn't work if you just memorize. So I hope you remember this guideline to begin with, and then we will start looking at the spectrum on next video. So see you next time.